Hello dear students, welcome you all. In this lecture, I am going to discuss about the triangular wave generator using operational amplifier. Triangular wave generator using operational amplifier. Right. Uh, so, uh, you might have remembered that uh, in case of integrator circuit, if the input of the integrator is a square wave, then its output is a triangular wave. We have seen it in the case of integrator. So it means I can design a triangular wave generator circuit by simply making the use of a integrator and a square wave generator. If I connect these two circuits, then I will get a triangular wave, right? First of all, I have to connect a square wave generator, and the output of the square wave generator will be given as an input to the integrator, right? This is you can see a square wave. Then this is given as an input to the integrator. So at the output of the integrator, we will get a triangular wave, right? So this is one method of designing this triangular wave generator using operational amplifier, right? In this way, we can produce triangular waves of the desired frequency. So here in this lecture, I am going to discuss another method, right? That uses a few components as compared to the method that is I described here by the combination of square wave generator and integrator, right? First of all, I will draw the circuit diagram, and then we will understand the working of the circuit diagram, and then in the end, we will derive the expression for the frequency of the triangular waves generated, right? So I am going to draw the circuit diagram that needs less components as compared to this method, right? So for it, we will start with the again operational amplifier. We will have a op-amp here. This op-amp is going to act as a comparator, right? This is the output of this comparator. This is then output. Then I have one more operational amplifier that is going to act as a integrator, right? So I have this one. This is the output of integrator. This is the path for feedback through a capacitor, right? And in this case also, we will have two inputs. Right. So this makes the circuit complete. Now I will induce some components here in this circuit, but first of all, let's make this path also. Right. Now we are going to induce the various circuit elements here in this circuit. This is for the supply, right? So I will have this one, and first of all, let's come to the value of supply. Plus BCC minus VEE. Again, same, plus BCC minus VEE. This is B output. This is positive. This is negative. This is positive. This is negative. This is virtual ground. And again here we have virtual ground, right? Now I'm going to induce the different resistances. This is one resistance. This is R2. This is R3. This is R1, right? And here we have a capacitor. So I'm going to this one. There, right? So now the circuit is complete. Now this is gain A of this amplifier, and this is A dash. Now this circuit is going to act as a comparator, right? This is on the feedback path, and this is the integrator. Great. So what I done here, that I told you in the beginning, that I can design a triangular wave generator by the combination of a square wave generator and a integrator. So actually that circuit require more components, electronic components. So I used this method for designing a triangular wave generator. Here I have simply used a comparator, right? Because we know very well that square wave generator is also a modified version of a comparator, right? Or we know we have seen in that case that it was basically a Schmitt trigger modification, and Schmitt trigger was what? It was a comparator. So here the same thing is, I'm using only a basic comparator and plus a integrator, right, with some additional circuit elements. So here this now this is sorry, let this is a what is the B output dash, and this is V output. So whatever output I will get here, I will get either plus V saturation or a minus V saturation. That is the value. I can say square wave of a comparator. This is the output we have seen in the case of a comparator. And what will be the output here? Output here will be a triangular wave. Because the output of a comparator is also kind of square wave. It swings, it moves between the two states, either plus V saturation or minus V saturation, depending upon the value which is higher. This input is higher or this input is higher. If this input is higher, then the output is in the negative saturation. If this input is higher, then it is in the positive saturation. So this circuit will generate these square waves. Then these square waves are applied to the integrator circuit. Then that circuit will further produce the triangular waves, and then these triangular waves are fed back to the this input here through the resistor R2 and R3. Now it means the net voltage appearing at this terminal, right? It is a combination of two things. One thing that is coming from here, right? And one thing that is coming from here. Now the combination of these two voltages, that will decide what voltage is appearing here. I can say that is V threshold. So this V threshold, or I can say BP, whatever you can say, that voltage will depend upon these two voltages. This one coming from here and this one coming from here. What is this? This I can say it is V ramp, because it is a kind of ramp. It can be either a positive rising ramp or negative ramp. So it will be plus minus B ramp. And what is this? Plus minus B saturation. So the voltage that appear here is a combination of these two, right? So if now you can see here this terminal of the op-amp is at ground, right? It means the potential at this terminal is 0. So if this terminal is slightly positive as compared to this terminal, in that case the output will be in the positive saturation, right? Suppose when the circuit is switched on, the output was in a positive saturation. So when the output was in positive saturation, the output of integrator, we know very well what is the output of integrator. It will be output of an integrator. B output is equal to integration 1 upon RC, right? V in dt, or negative sign, negative because integrator. So what it will be? It will be a negative going ramp, right? This ramp, when the output is a input here is a positive saturation. V in is a positive saturation voltage, then this output will be a negative going ramp, right? This one, clear? According to this equation, we have seen it in the case of integrators, right? Now this negative going ramp, B ramp negative, this is applied to this terminal, right? Now this negative going ramp, right, I can say minus V ramp, and this positive saturation voltage coming plus B saturation coming from here, they will join together and they will form the resulting voltage at this point. Now this negative going ramp, this is going in this way, it will continue till the voltage at this terminal, ultimately it will become 0 when these two will cancel out one another, and at that time the net voltage at this point will become 0. Now then after, the voltage at this point will try to go below 0 because negative ramp is rising, it is going further. Now when the potential or voltage at this point slightly goes below 0 as compared to this, then what will be the result? Now the potential or voltage or signal at this input is higher as compared to this one, so the output will swing into minus V saturation. And when the output will swing into negative V saturation, what is the output of this? This output will be now positive rising ramp, right? It will now start rising in the positive direction. It will become plus V ramp. Then this plus V ramp will come here and join here with this negative saturation. Again the same thing. This positive rising ramp will continue to rise till the point when the potential at this point becomes 0. Then after, it will start go in the positive direction. It try to become positive, but as it become positive, now it is 0, it is positive, this is now higher than this. Again the output of this integrator will force to the negative saturation. So this process will continue and you will get a triangular wave at the output of this circuit. Clear? This is shown here, right? So this is the working of this entire circuit. I can show you the waveform, resulting waveform here. So to draw the resulting waveform, This is the output of a first circuit comparator. This is the output of a comparator. Time, and this is voltage. This is what B output dash that I have shown you here, right? B output dash. Now this is 0, right? This point is plus B saturation, and this point is a minus V saturation. Now if I look at the ramp voltage, let this is sorry, minus V ramp maximum and plus V ramp, right? So what will be the effect? Yeah. Right, in this way. Now you can see when the output B output dash was in positive saturation, the output of this integrator, this is the output of integrator. I can say B output, clear? This is a negative going ramp, right? Now when this try to goes below this point, right? You can see from here, then at this point it is maximum, right? So you can see from here that I told you that when this ramp wants to go beyond this point, you can say the output. Now output of which this it changes from a plus V saturation to minus V saturation. It is clear from here. Now when it is in negative saturation, now the ramp again want to rise, but it now want to rise in the positive direction. So as it reaches here at this point, clear, as it reaches here, now if it want to go beyond this point, what will be the value? Now the output will be forced to the positive saturation. You can see here, right? If the ramp want to go beyond this point, then what will be the result? I have explained here. If the ramp want to go beyond this point, right, then what will the result? The result will be the output will swing to the positive saturation. Clear? Because if ramp want to become more than this value, right, it means the output of this circuit will become plus V saturation. You can see here. So again this cycle will repeat, it will continue, and you will get this. Right, so you can say you will get continuous in this way. These are the outputs, right? So this is the output. This is you can see here clearly that it is a triangular wave, right? You can see here that it is a triangular. What is this? Sorry, right? This one, it is a triangular, right? So I explained you here that what is happening in this circuit. Initially B output this was in positive saturation. So when it was in positive saturation, this ramp was a negative rising ramp, right? It continues to rise. It reaches a point minus V ramp. When it reaches at this point, the net voltage at this terminal become 0. Then it want to go further, right, in this direction. But then if want to go further, then it becomes below than 0 potential, right? In that case this potential becomes higher, right? So it means the output will become a negative saturation. You can see now it is higher, so output is in a negative plus negative B saturation, right? Now when it is in negative V saturation, this ramp will be now a positive ramp, rising ramp. It will continue to rise. Ultimately, it will reach a value at this point when again the voltage at this terminal become 0. Now it further go more positive. It want to become more positive. As it want to become more positive, what will be the result? Now the voltage at this terminal becomes positive slightly with respect to the 0. So again this will become higher, so the output will be in a positive saturation. You can see. So this process will continue, and you will get a you can see you will get a triangular wave, right? So if I look at the time period of this triangular wave, then you can see from here it will be from here to here. You can take it like that. You have this time period t starting from here to here. Clear? So it is t. Yeah. Or you can even take from here to here. The same thing is there. Here to here. Clear? Going from negative V ramp to positive V ramp, and then again coming back. It is again same thing. Clear? So now I will like to find the peak to peak voltage as well as the frequency of these triangular waves generated here. Now in order to find the peak to peak voltages, right? Peak to peak voltage, this one, right? I will use the Kirchhoff's junction rule at this junction, right? Let current I is going from I1 is going from here, and I2 is coming from here. I2. Clear? Now we can say these two currents are coming at this point, but the resultant current that should go toward this side, right? But that current is nearly equal to 0, right? We know from the theory of op-amps. So it means this current should be exactly equal and opposite to this current, right? Only then it is possible, right? If I consider that the net current here is equal to 0, right? Appearing at this terminal is equal to 0. So I can say B. Now what is the value of the current here due to this negative V ramp? It is, I can say I1 is equal to I2 in this circuit. So I can say B ramp upon R2 must be equal to this is negative ramp, right? Is equal to negative of B saturation plus, right, divided by R3. You can see from here it was plus V saturation initially, right? Negative because these two currents are opposite. That's why they are cancelling each other, right? And this is B negative ramp upon R2. So I can say B ramp negative, that is equal to minus R2 upon R3 B saturation plus. Clear? So this is the value of a negative V ramp. Similarly, we can find the value of a positive ramp, right? B plus ramp. It will be the same, right? But the difference will be minus R2 upon R3, but the difference is B negative saturation, right? Now, what is a peak to peak voltage? Peak to peak voltage means B plus ramp minus, or we can say minus minus, you can take plus, minus B negative ramp, right? So this is the B peak to peak voltage. Peak to peak means from here to here, or we can say from here to here, right? Peak to peak. So if I put these two values here, what I will get? B peak to peak, B output peak to peak, or we can say B peak to peak is equal to now when you will do this all, what you will get? You will get this becomes plus R2 upon R3 negative B saturation, right? Sorry, I mistaken here. It is not negative because we have already taken V negative ramp. So it will be now So no, it was right. I have mistaken. Sorry for it. It will be negative. It will be negative. It was all right. So it will become this. Now this was one term. Minus minus becomes plus into minus R2 upon R3 into B negative saturation. Now what it becomes? It becomes 2 R2 upon R3, right? 2 R2 upon R3, right? Uh, Not 2, it was 2 will come in the last. I mistaken here again. R2 upon R3 common, right? Into minus B saturation plus B saturation minus, right? Now we know plus B saturation is equal to minus B saturation, plus minus 12 volt or 15 volt. So it becomes 2. I can say that is equal to B plus saturation is equal to B minus saturation is equal to B saturation, I will say. So it becomes 2V saturation. So minus 2 R2 upon R3 B saturation, right? This is V peak to peak. If I take magnitude, this sign will get removed. I will get peak to peak voltage is equal to 2 R2 upon R3 B saturation. This is the value of this B peak to peak, right? That we are getting here, right? Now, we'll find the expression for the frequency. So, to calculate the frequency of the triangular wave, I will make the use of the this graph. The net time taken by this triangular wave from going from minus V ramp to plus V ramp. You can see from here minus V ramp to plus V ramp. It is, if I consider this entire time as the time period, obviously then it is T by 2. Clear? T by 2. You can see from here this is the total time, then from here to here it is T by 2, and in this interval or during this time the output was in a negative, output of this was in a negative saturation. So input of the integrator was a minus V saturation. So I will make the use of this equation. So we know B output, right, peak to peak, that is equal to minus 1 upon R1 C1, R1 C, not C1, whatever. Yes, I have taken here C. I have not written here. It is C. You can say C1, R1 C1. So it is R1 C1 integration 0 to T by 2. What is V in? Now V in is a negative V saturation, right? V saturation, what it is a negative, right? dt, right? So when you will simplify it, you will do the integration. Then after simplification, you will get t is equal to, you can do it, 2 R1 C1 B output peak to peak, right, divided by B saturation. Clear? It was negative V saturation, so understood negative V saturation is equal to V saturation. So this T is equal to this. Now putting the value of B output peak to peak, that is this one. So you can write 2 R1 C1 upon B saturation into V peak to peak 2 R2 upon R3 into V saturation. You get cancelled. You get T is equal to 4 R1 R2 C 1 upon R3, right? This is the time period, right here, clear? So then after frequency will obviously equal to 1 upon time period. So 1 upon means R3 upon 4 R1 R2 C1, R1 R2 C1. Yes, it is all right. So this is the expression for the frequency of these triangular waves generated by this particular circuit, right? You can see here that the frequency of these waves depend upon the value of R1 R2 C1 and R3, right? R1 R2 R3 and C1. So this is all about this triangular wave generator. It is very, very important. Even you can design this circuit on a breadboard, and then you can verify this by using a CRO. You will get the same results, right? You can change the frequency by changing the value of these resistances and capacitance, right? So thank you very much.